Hi everyone, I'm Nitin. I work as a senior consultant with ThoughtWorks. So currently, I'm working with a project in the data engineering field, where we're developing a system for data discovery and data governance. So I'll be walking you through the same use case today, and I'll be talking about how we utilize Azure Cognitive Search to build the data discovery service, and we'll talk about various terminologies and various methods to optimize the data in the cognitive search engine. I'll quickly share my screen now. All right. Now, what Microsoft Azure Cognitive Search Engine is, right? We'll talk briefly about it. So, Cognitive Search Engine is a search as a service platform available on Microsoft Azure Cloud. Apart from being a search engine, it also has integration with other Azure Cognitive services. For instance, OCR extraction, key phrase extraction, and auto completion also, right? Now, so if we talk about other features available in cognitive search, it also provides you geospatial search. So apart from geospatial search, it also provides you facet capabilities. I will quickly talk about the architecture of Azure Cognitive Search Engine. So Azure Cognitive Search Engine composes of three primary components. One is the indexing engine. Then we have the index store, where the index data is stored in form of inverted indexes. And apart from this, we have a query engine. The Azure Cognitive Search Index, it provides you integration in the form of other indexers. So whatever data sources we can think about in Microsoft Azure, whether be it SQL Server, Cosmos DB, it provides you indexers that can crawl data directly from those data sources. Apart from indexers, like we also have the capability to upload data directly into cognitive search using the push-based mechanism. I'll now quickly walk you through the UI of cognitive search. So this is how the UI of a cognitive search engine looks like. Underneath the indexes section, you can see the set of indexes that you have created for the cognitive search. Indexers, if you create any to crawl the data, you'll find them over here. Going back to the index definition, if you look at the fields, you'll be able to look at all the fields that are created in the index and which all are searchable, filterable. All those properties are defined over here. The Search Explorer provides you the capability to invoke the REST APIs that Cognitive Search Engine provides you, so that you can query on the data easily. Now, talking about the integration part, so Cognitive Search Engine provides you integration in majorly various programming languages, whether be it Java, .NET, Python. All these programming languages have their integration. Integration with cognitive search to create an index is pretty straightforward. All you have to just create is a model, annotate all the properties with the cognitive search engine annotations. So I'll quickly talk about few of those. One is a simple field. Simple field indicates that the property won't be indexed. It won't be used for searching the data. Apart from that, if you create a searchable field, as the name indicates, is used for searching data. You can define properties as in if the property is sortable, searchable. Now we'll talk about the analyzers also, maybe in the next slide, but it provides you a capability to define like which analyzer do you want to split the data into tokens and store that into the cognitive search engine. So this is how you define the definition of an index. Creation of an index is also pretty straightforward. I'll go to the example here. So it provides you a search index client, which helps you to build search fields using the index using the POJO definition that we have already discussed. You just have to invoke a create index method in order to create the cognitive search index into the store, right? Now back to the slide. I'll talk about the basic features and capabilities available. It provides you a search engine for full text search. It provides you rich text analysis and AI enrichment. It supports multiple kinds of query formats. One is a simple Lucene query, and one is the full Lucene query syntax. As we told, like, it has SDKs available in all programming languages. And it also has integration with machine learning services in Microsoft Azure environment. Now, let's quickly talk about, like, we have already talked about how do we create an index. Now we'll quickly walk you through how do we optimize the data in an index, right? Now, before we start talking about optimizing an index, we will have to look about how do we do the capacity planning for the index, right? So Azure Cognitive Search Index is built in the form of storage units, where the number of storage units provisioned are equal to number of partitions created for the data into the number of replicas that we are creating for data. Like, more the number of replicas, it means that we have higher availability of cognitive search engine. So as you can see over here, like, if you have, let's say you have 2 partitions, you have 2 replicas, then you create a total of 4 storage units. So the maximum storage units that get created are maximum of 36 units supported in cognitive search. And the amount of data a partition can store, it all depends upon the plan that we have chosen. So looking at the various plans, it provides you free, basic, standard, and the most optimum plan is the storage optimized. The standard supports 20 GB per partition, whereas a storage optimized one supports 2 terabyte per partition. These are the cost estimates for the cognitive search engine. So if you want to have a look at the cognitive search demo for creating a cognitive search index, it's available on my GitHub account. Azure Search Documents is the library supported by Microsoft for this. Now, like, we have already talked about how do we create a new index. So once an index has been created, like, we annotate every field with annotations to specify, like, this is the analyzer that I have to create for separating the lexical tokens out of the text. Now let's talk about how do we identify which is the right language analyzer, right? If you don't specify any analyzer for the cognitive search index fields, by default, it supports Lucene English Analyzer. But we are free to choose any custom analyzer for us. So if we look at the diagram here, like, it supports multiple programming languages. So there is an option for Microsoft Analyzer, and at the same time, there is a Lucene Analyzer also, right? Now, having said that, there are pros and cons of using a Lucene Analyzer, and there are pros and cons of using a Microsoft Analyzer for the specific language. I'll quickly iterate it with the example of the English language analyzer, which is en.Microsoft Analyzer. So en.Microsoft Analyzer, it provides you options to split the text better than what the Lucene Analyzer provides you. So basically, the Lucene language analyzer, it splits the data on the basis of spaces, tabs, commas, whereas Microsoft Analyzer provides you more rich feature. If we say, like, if you have properties such as SQL_server, right? So Lucene Analyzer only provides you SQL_server as the term, whereas Microsoft Analyzer also splits on underscores. So if we say Microsoft Analyzer, it provides you more rich tokens as compared to Lucene Analyzer, but it has a downside that Microsoft Analyzer, it takes more time to index the data into the index, right? So when you start importing your data from maybe a SQL server into a cognitive search engine, it will consume more time to index the data. So this is the positives and drawbacks of using an analyzer. So it's something that you have to decide when creating an index in cognitive search. Now, so when you create an analyzer for a property, basically the search and index analyzers both are the same, right? Now, you could run into scenarios where maybe if you want to store tokens, maybe you can use Azure Microsoft Analyzer, because you want to have rich set of tokens. But on the search side, you'll want that, okay, I don't want to split the tokens. I just want to search for the entire term, right? For those kind of scenarios, you could choose a separate search analyzer, and you can choose a different index analyzer, right? So going back to the same diagram, so when the data gets indexed, SQL underscore server gets broken into SQL server and SQL underscore server. So 3 tokens are stored into the index structure. Whereas when you start searching for SQL, you'll use the Lucene analyzer, and it will directly search for SQL in the indexing structure, in the inverted index, right? So there could be scenarios in your code base or your application where you could have to choose for a different analyzer, and it will provide you a better response time for searching the data also. Now, cognitive search also supports for custom analyzer. So we have already talked about multiple analyzers, whether be it Microsoft or Lucene, but you could come into scenarios where the data format that you're storing, any of the analyzers already provided by Microsoft or Lucene, they don't fit your purpose, right? So in those kind of scenarios, you'll want to create a custom analyzer. Creating a custom analyzer is pretty straightforward. Just create a character filter, which will filter out all the unnecessary characters out of your data. Tokenizer, you could use in some pre-built rules, or create regular expressions to break down the data into lexical tokens. And then you'll have to use a token filter, which will remove unnecessary words like A and the, or maybe some unnecessary characters that you have in your data. So using all these steps, you'll be able to create a custom analyzer, and then you'll be able to associate it with your properties and index the data. Now, so let's assume you have created an index. You have already associated all the analyzers with those. But there could be scenarios where even despite having all the rich set of tokens into the index, you're not able to search for the exact data that you're trying to search for, right? Users like if we talk about users, the users don't have idea like what kind of data is stored in the index, and what exactly the term that a user should be searching for, right? This is primarily because there are synonyms for every text stored in the indexes also. I'll give you an example. Like for instance, if you're storing United States of America in your index data, right? Data could be stored in the form of USA, United States of America, and your users can also search for any of these terms, right? So in those kind of scenarios, you can create a synonym map into your index, put all these rules in the synonym map, and then basically if a user is searching for USA and the document has United States, he would still be able to get the data out of those documents, right? So these are called equivalency kind of maps. So equivalency kind of maps, it creates an equivalency between all these terms, so that if a user is searching for any of those terms, and he'll be able to get all those documents out of the search results. Other kind of synonyms that you can create in your index are called explicit synonyms. Now, what are explicit synonyms? So these are useful in those kind of scenarios where you only have a specific term stored in the database, but a user can search for any of the other terms, right? So let's say you have only CA stored as California in your index structure, whereas users are either searching for California, Calif, or CA. So in those kind of scenarios, you just have to create an explicit synonym map. So explicit synonym map will convert all these values during the searching into the destination field, and then it will query for the data in the index row. So this is how synonyms come to your rescue when you want to search for data that has multiple versions in the index data. So you have synonyms, you already have set up your analyzers, but you'll run into situations where multiple properties have different weightages while searching, right? Coming back to the same example that I illustrated in the GitHub repository, like let's say I'm indexing the data of data sets within the cloud platform, and I'll want to have different kind of weightages for the data, right? So let's assume in my JSON body, I have a data set name, I have a description, I have a steward name, right? So when a user comes to my portal, he'll say, I'm more interested in searching for data sets names as compared to the description, or maybe a person who owns a data set, right? So in those kind of scenarios, we can assign some weightages to the properties. So when adding an annotation at the rate searchable, so that just provides you that this property is searchable. But once you're creating an index, you can create a scoring profile and then associate weights for every property. In that scenarios, when searching a data, name will get higher weightage as compared to the other properties. For the nested properties have to be given weightage in the form of parent object followed by the child object. So if you have a schema under a data set, schema slash, then the schema has a column name. So schema slash column name has to be given the weightage, not the parent object. Now this is about a scoring profile, but users will still come with scenarios where we'll say, okay, for one kind of scenario, I want to search for data sets. Maybe in the other kind of scenarios, I want to search only for columns. I don't want to search for anything about data sets, right? So you can create multiple scoring profiles. You can set them on the index data, but you'll have to set up one default profile. So let's assume we set data set name as the default profile. So if you want to switch from one profile to another, we can specify it in the request body. And then we can specify the search term. So on the basis of that, we'll be able to switch scoring profile and optimize our search results. So with these scoring profiles, we have already talked about static weights, right? But there could be scenarios where maybe we want to evaluate something. Let's assume if a document has been added recently, we want to weight those documents in the higher weightage, right? So scoring functions are also provided in the scoring profile. For the properties, you can create scoring functions, and based on the result of scoring functions, your data sets or the documents can be weighted accordingly, right? So some examples of scoring functions are, for example, magnitude of an integer field. It specifies that how the search results should look like in the search results. Freshness of data, labels. Let's assume you have some labels on the data. So those will be weighted higher. And similarly, distance. Let's assume you have distance stored in the index. So if I'm a user, I'm maybe searching from Delhi, right? I want to see search results nearby Delhi location. So those distance functions can be applied on the scoring profile, and the search results can be optimized accordingly. Now, index is all created. Now, how do we query the data? That is something that we also have to consider while optimizing our search results, right? Now, if we talk about multiple queries supported in cognitive search engine, one is a simple query, one is a fully seen query. I'll just talk with an example. How does a simple query look like, and how does a fully seen query look like? Now, let's assume you just invoke the REST API. You want to search for a data set named user login, right? In the search property, you'll pass search is equal to user underscore login. So that way, the cognitive search engine would search for terms that contain user and login, right? So when a simple query is executed, so the queries actually go through the analyzer first. So as we talked, there is a search analyzer also, right? Search terms go through the analyzer. They are converted into lower text case. They undergo lexical analysis. So let's assume for dataset name, if we use Microsoft Analyzer will break user underscore login into user login, and it will also return the user login as a complete keyword. Then it will search for data in the index structure, and then it will return back to the search results, right? But there could be scenarios that you're not interested in getting data sets starting with user or having login as a keyword in it, right? You'll want to search for entire term. For instance, I'll say I want to search for a steward named Sheldon Cooper, right? All you have to do is enclose the term in the double quotes, and it will search for the entire lexical token. It will not search for individual tokens in the index. So simple queries are basically useful for scenarios where you want to do a full text searches, right? You don't have to exactly look for data, specific data, right? So those kind of scenarios, simple query is just sufficient. But you'll have scenarios in your application where maybe you want to do exact type of matches, right? Maybe you do a wildcard search, or maybe there could be scenarios you mistype something, you want to do a fuzzy search, right? Maybe you want to search on the basis of regular expression. So simple query doesn't provide you a capability to do those kind of searches. It is in those kind of scenarios that full Lucene query comes to your advantage. Now, full Lucene query, apart from what is supported in simple query, it provides you additional capabilities like wildcard search. So for wildcard searches are enclosed between the slash symbols followed by dot and star to indicate if you are searching for one or more terms, right? So if I say I want to search for a data set name colon followed by the wildcard characters here. Fuzzy search is used for scenarios where you could say that I'm doing a kind of a search where maybe I might have mistyped something. I want to search the data in a fuzzy manner so that it can replace one character with something else and then also match the data, right? For instance, if I'm searching for Paul and I'm including a tilde sign here, right? It indicates I can have an error up to one character and I can replace it with with any of these characters in the steward name, right? So if I search for Paul, it will also return me a name which has Saul, right? SAUL will also return as a matched item in these kind of scenarios. Now, talking about regular expressions are somewhat similar to wildcard searches, but it provides you a capability to write in the regular expression syntax exactly. So if we say I'm searching for a data set name with a description, so I'll be able to search for a motel, I'll be able to search for a hotel. So these kind of matches would these regular expression will give you match two tokens for motel and hotel, and you'll be able to get the data out of the index easily. Now, apart from using the queries, whether be it simple or dynamic, we also have another thing called a term boosting factor. So when we have talked about static scoring profiles, they provide you static weights on the individual fields, right? But you'll have those kind of scenarios in your search queries where you want to dynamically change the weightage of the properties, right? So this is called a term boosting. So term boosting refers to increasing weightage of columns and terms specifically at runtime as opposed to static weights as supported in the scoring profiles. I'll quote it with an example here. So let's assume you have name, description, and other properties, right, in the index data. So you want to search for name where the property it matches user login exactly. You want to provide it a 10 weightage. If the name matches user login followed by some other characters, I want to give it a lower weightage. And similarly for description, if a document matches user login exactly, I want to still give it a lower weightage. So these kind of queries can be executed by term boosting, but term boosting can only be applied in full Lucene queries. That is something that we have to keep in mind while executing these. Now we'll talk about what are the impact of regex queries and term boosting, right? So whatever feature we use in a cognitive search engine, like all those have some wins, they also have some impacts, right? Talking about the wins, regex queries, they provide you an exact match. Data would be sorted as per your expectations, right? Whereas if we talk about the impacts, so the analyzers are bypassed when searching with regex queries. So you'll be able to get the exact matches, but similar kind of matches, those would be ignored. Another performance impact on using regex queries extensively is that it uses a full index scan as compared to a peak. So full index scan, like similar to what we see in our SQL databases also, right? Seek operations are faster as compared to scans. So a full index scan will have a higher response time as compared to operations using a peak operation. So another kind of scenarios like columns, if they have some lowest weightage and they don't have very common terms, right? Those kind of queries will take a longer time to return the response. So as we talked about the previous example, So if you say like user login, description, or maybe if you say if you have a third property also, steward, right, in the property. So if you're searching for a name that is not very common in the data sets also, so those kind of queries will first look for data in user login because they have the highest weightage, right? Once it doesn't get the data in all these, it will go back to the last property, right? So those kind of queries will have a higher response time because they have a very lower weightage as compared to the rest of the properties. Filters and faceted searches, right? So far, like whatever queries we have executed, we are trying to search for data within the entire index, right? So data is getting searched in all the partitions, all the replicas, right? Now you'll have scenarios within your application, right, where you just want to search for a data that is subset of specific data. So filters come to our rescue, right? A cognitive search API provides you filter capability so that you can narrow down your search results also. I'll talk about the example that we have talked earlier, right? We have set of data sets into the cognitive search engine. Like you could have data sets which are maybe a table, data sets which are maybe blobs, data sets which are maybe Parquet. They're stored somewhere else, right? So you'll want to search for data sets. Maybe I want to search for a user login table which exists in the form of a blob on Microsoft Azure, right? I don't want to search for on-premise data. For those kind of scenarios, I could introduce filters in the form of OData queries. So you could specify data set type equals table and maybe location equals to Azure. This is how your filters properties are executed, right? But the real problem lies behind how does a user know what to filter for data, right? He doesn't know what data exists in the database. What exists in the index also, right? Now, for those kind of scenarios, facets is a feature provided by cognitive search where the index will return you the unique set of values that exist in the index store. So let's assume if I say a data set type, when executing a wildcard query on my entire database, I could get set of facets for data set types. It will return me table, blob, Parquet, all those different kind of unique values. Now, when I execute my next query, I can specify to cognitive search, okay, I know like it has table. I just want to concentrate on tables now, right? So you can specify table data set type equals table in the next query and then filter your data accordingly, right? So that way you'll be able to narrow down your searches and you'll be able to get the exact data that you want, that you're trying to achieve. Facets, now, like we have already seen like what advantage that it brings to your search queries, but it also has an impact on the index, right? Facets, since these are unique values in the index, right? So there is an overhead associated with it. A facet is a tuple consisting of like what is the unique value. If you say table is a unique value, and how many data sets or documents which have table in them will also get a count, right? So those values are have an impact on the index while executing the queries. So there are some recommendations like how should you load the facet data also out of your index. So impacts versus gains of facets, like they give you an insight of what exactly the data exists in your index. It makes it easy to search the query data, right? Impact is like they have a cost. So if you do a query with the facets, you want to return the facets also out in the response. So those will be very costly operations. So there are some recommendations over use of facets in an index. Use facetable annotations on properties that have low cardinality. So if I say a data set type, it hardly has 3 or 4 or maybe 5 properties, right? A table, blob, or something like that. So those kind of properties are good for using a facetable annotation. Whereas if I say I want to search, I want to add this property even on the dataset names, right? Because dataset names, those doesn't have a low cardinality number. You'll have enormous number of datasets in the unique dataset names in the cognitive search engine, right? So you don't have to use these annotations on those kind of properties. And other thing is, we recommend using executing the facets on a search operation only when executing the first page of a search operation. So because facet values won't change when you navigate from first page to the other page. So it's better that we only execute it once, and for better performance, a recommendation is to cache all these facets values for searching. Now there is something called how does Microsoft Cognitive Search get you the data in relevance, right? So it uses a similarity algorithm called BM25. So this is a static algorithm that we cannot modify in Cognitive Search Engine. There was another version of Classic, but that has been deprecated and replaced by BM25. But what we can do with this similarity algorithm is we can fine tune the parameters, right? BM25 algorithm, it provides you two parameters, which is called K1 and B. So K1 indicates, so if you have, if you're matching a search term in a document, right? How does the frequency of that search term in the document impact its relevance, right? So if I say I'm searching for user underscore login, you have user underscore login in a document multiple times. So will that keyword existing multiple times have an impact on the search? K1 is a parameter that you can fine tune, right? It ranges from 0 to 3.0, and the default parameter value is 1.2. The other parameter is called B, which indicates how does the normalization happen on the length of a document. So if you say you have a keyword existing maybe 1,000 times in the document, but your document length is maybe 17 MB, right? And maybe you have another document which is maybe of a few KBs range. It also has 50 times the search term, right? How does the normalization happen on the data? Will the document that has maybe 16 MB of data, will it get a higher relevance, or a document that is only a few KBs will get more relevance, right? B is a parameter that you can fine tune while searching the results. It ranges from 0 to 1.0, and the default is 0.75. So higher the value, it indicates that length of a document has an impact on the search. Whereas if you set it to 0, so it means like a document with a length of few KBs and a document with 16 MBs, like they both have equal weightage. They don't make an impact on that. So this is how you can modify your similarity algorithm to get more fine tune of the data from the index now. So when we talked about scoring statistics, right? Scorings are calculated on data. Your documents are relatively positioned in the search results, right? But how are those scores, or maybe facets also, right? Facets also give you like what are the unique values that exist in your entire index. But as we discussed in our first few slides, right? The data is partitioned into multiple shards, right? So basically, when a query is executed on a search index, it gets executed in each of these shards individually, and then the results are aggregated and then returned back to the end user, right? Now you could run into scenarios like where your facet values, you don't get all these results back into in the response, right? These generally happen when you don't have a very large data. So generally a data gets equally added into all these shards. But if you have a less data, let's say in the range of a few GBs, right? So you could come into run into scenarios, maybe one shard has more data, the other one has less data, and in those kind of scenarios you'll get different search results also. Maybe you have a distinct value in one of those shards, but it is not getting returned in the form of facets to you, right? So in those kind of scenarios, you could use scoring statistics global. So you'll have to pass in this parameter to Cognitive Search Engine. So Cognitive Search Engine will calculate all these statistics at the global level. Having said that, like it has a performance impact, can only be used in scenarios where data is in the form of few GBs. So these were the performance suggestions. So now, apart from these suggestions, so So these are some performance tips that Microsoft also recommends when creating a search index. So you'll have to keep in mind what is the index size and schema. So cognitive search, like it provides the capability to index multiple fields, but you have to be cautious, like which all fields need to be filterable, like which all needs to be facetable, because if you add all the searchable fields, index has to calculate the values on all those properties, right? You have to be cautious about selecting the number of fields. So don't go and create all these fields with a searchable attribute. It has a performance impact. Now, simple versus complex types also. So Microsoft recommends use simple data types, whether be it int or string, as compared to nested properties. Like nested properties are supported, but they do have a performance impact on the search queries. Now, when executing maybe fully seen queries, you have to be cautious about choosing the number of search fields for searching. And you also have to look about the amount of data getting returned. So if you are returning maybe 1000 documents in a search query, that will have a higher response time as compared to less documents getting returned. And the other thing to look is high skip values. So maybe if you are searching for or for some search results on the 100th page, right? That will generate a higher response time as compared to searching for data on the first page of the index. So these are some basic recommendations from our experience on building data using cognitive search engine, and these are some recommendations that Microsoft is recommending to include it in your search engine, right? Now we'll also talk about upcoming features in cognitive search engine. So currently cognitive search engine, it supports using a URL and an API key to integrate with your cognitive search engine, through your APIs, right? So now Azure AD based authentication is something that is in preview and would be released this year. So what you can do, you can apply role based authentication on cognitive search engine, and then you can use your service principals associated with your web applications to interact with the cognitive search data. Apart from the lexical searches that we have talked about, other thing is called a semantic search. So semantic search, it will look for semantics in the data. So this is also a preview feature and would be soon provided by Microsoft in the coming year. So these are the documentations and references. So these talk about introduction, REST APIs, capacity planning, indexers. These are the links for the Azure Search documents in Java, and this is the sample code base that you can utilize to get started with the cognitive search engine. And as we said, we are all looking forward to work with you. Thank you everyone for your time. If we have any questions, we can ask them in the Q&A section now.